Welcome to the third and final video on the various renewable energy technologies. So far we've been looking at the sun as the main source of energy. Solar energy is used directly in photovoltaics, and additionally solar radiation evaporates water, generates temperature gradients in the atmosphere, and fuels organic life through photosynthesis, powering the renewable hydropower, wind power, and bioenergy technologies. We have, however, another renewable source of energy that is right below us, planet Earth. Millions of years ago, planet Earth was nothing but a hot globe of molten rock. Lucky for us, the Earth has cooled down to a point where you don't burn your feet when you go outside. That said, the Earth's crust is still only a very thin layer of cold rock, basically floating on a sea of lava. If we go down a few kilometers, we can already start using the Earth's heat. The general principle of geothermal energy is relatively simple. Hot water is pumped up from an underground reservoir. The heat in the groundwater is extracted with a heat exchanger. That heat is then used in a similar fashion as in a solar thermal plant, a biomass plant, or a nuclear power plant, using a conventional steam turbine and generator to convert thermal to mechanical energy and then to electrical energy. The cooled water is re-injected in the ground at a different location. The water will permeate through the rock, collecting in the reservoir all the while heating up again. The depth of the reservoir can vary between several hundreds of meters up to several kilometers. The underground area from which the water is extracted should be large enough to facilitate continuous hot water extraction and to avoid the hot water from mixing with the injected cold water. Often, multiple extraction holes are drilled with a large distance between them. The streams are in a closed circle to avoid pollution of the groundwater. Geothermal energy can also be used on a small private scale. In that case, geothermal refers to the heating and cooling of a house using pipes in the Earth's crust. The Earth's crust has a constant temperature. During winter, the Earth's crust is warmer than the ambient air, while in the summer the Earth's crust is cooler than the ambient temperature. Losses in a geothermal system are mainly the result of heat exchange efficiencies between the water reservoir and the rock beneath the crust. Apart from that, there is a heat loss in the pipes and in the heat exchanger and conversion losses in the turbine and generator. Additionally, since the water needs to be pumped up, there are electrical pumping losses due to friction in the pipes. For economic feasibility, the hot water reservoir should be close to the surface so that the frictional and thermal losses in the pipes are minimal. Such reservoirs can be found, for instance, in Iceland, which lies on a fault line. Exploitation of such a hot water reservoir close to the surface can be observed here in a geothermal plant close to Reykjavik. Geothermal energy production doesn't have an intermittent character. A main advantage of geothermal energy is therefore that the plant can act as a base load for the electricity grid, which eliminates the need for gas and coal plants. Another advantage is the long average lifetime of a geothermal plant of at least 30 years. After that, the heat reservoir generally needs time to recover or will produce a lot less power. Finally, since the actual heat collection will take place underground, most of the ground above remains accessible. The land use of geothermal energy is therefore very small. However, not all locations are suitable for geothermal power plants. And additionally, drilling to find the right rock type can be very expensive. So by now you understand the very basics of the 5 most important renewable energy technologies. Let's now compare the different renewable energy technologies using some relevant metrics to put them in perspective. We will start with the total power that is available for conversion. The primary energy potential of solar on land is about 23,000 terawatts, which is about 1,000 times the global power demand in 2040. The fact that most sources of renewable energy are a derivative of solar radiation is reflected in their respective potentials, which are only a fraction of the solar energy potential. The primary potential of geothermal is also only enough to cover a small fraction of the global power demand. Another way to look at the technologies is by comparing the power density that each can generate. In this visual, the area required to meet the global electricity demand in 2040 is indicated, taking into account the available power density, the system efficiencies, capacity factors, and water catchment area in the case of hydro. It is clear that satisfying demand through photovoltaics, or a combination of PV and wind, is most viable in terms of generated power density. So why then don't we simply focus our collective efforts on solar PV? This has to do with the intermittency, so the day-night and seasonal variations of PV power generation. The same is true for wind energy. Fortunately though, the intermittency of wind and solar power generation match well together. That is, on average, wind power generation is higher during nights and winters, while solar power generation is higher during days and summers. Still, power generation from these sources is not continuous, which is why geothermal, hydropower and biomass technologies remain of such interest despite much lower primary energy potentials and generated power densities. They can provide both a continuous source of electricity as well as a means of energy storage. Additionally, there's always the local energy power potential to consider. Why not use geothermal if you're sitting on a geyser like in Iceland, or use hydropower when water basins and high difference are abundantly available like in Norway? Now let's look at some other metrics. Here we compare the levelized cost of electricity, or LCOE, of different renewable energy technologies. The LCOE is an economic assessment of the average total cost to build and operate a power generating system divided by the total energy output of the system over its entire lifetime. The levelized cost of electricity of a coal plant, for instance, according to the US Energy Information Administration, is between $70 and $98 per megawatt hour. The LCOE of a combined cycle natural gas plant is about half of that. Now let's look at the LCOE of different renewable energy technologies. While the LCOE of biomass is quite high, the LCOE of the other renewable technologies are lower than that of a coal plant. Moreover, the LCOE of geothermal, solar and wind are on par with a natural gas plant. PV even has lower LCOE in many regions with favorable levels of solar radiation. Finally, we compare renewable technologies using a slightly more complex metric from the 2022 report from the Intergovernmental Panel on Climate Change, or the IPCC. This metric shows the potential reduction in greenhouse gas emissions by implementing a certain renewable energy technology. The colors indicate the costs of implementing the technology. Both are determined in reference to currently implemented technology. The horizontal bars show the reduced emissions in gigaton of CO2 equivalent per year. The CO2 equivalent does not only include CO2 emissions, but also other greenhouse gas emissions, corrected with their respective global warming potentials in reference to CO2. The visual indicates that emission reductions can be realized using any of the renewable energy technologies we discussed. The yellow color indicates that it is cheaper to realize emission reductions through geothermal and hydropower than it is using biomass or by applying carbon capture as storage systems to existing infrastructure. Most notably though are the large emissions reductions that can be achieved through wind and solar. Moreover, the blue color indicates that these emission reductions can be achieved at lower costs than the current reference infrastructure. So in summary, in these 3 videos we have provided a brief overview of the dominant renewable energy technologies. We looked at their respective working principles, their advantages and limitations, and compared them using some different metrics, including the energy potential, the generated power density, the levelized cost of electricity, and the carbon footprint. I would like to point out that a complete course on the different renewable energy technologies available from the DelftX team entitled Sustainable Energy, Design a Renewable Future. In the next video we'll start with solar energy in earnest by looking at the different aspects of solar radiation.